January 5, 1943. Off Guadalcanal, gunner's mate second-class Tom Wheeler crouches behind the aft 5-inch mount aboard the light cruiser USS Helena, watching a Japanese Naval dive bomber pull out of its attack run against the destroyer formation ahead. The aircraft, painted in mottled green and grey, banks hard to the left, accelerating away at nearly 250 miles per hour. Through the salt spray and gun smoke, Wheeler can see the Naval's fixed landing gear and greenhouse canopy growing smaller with each passing second. His gun captain, Chief Petty Officer Martin Desmond, barks the command Wheeler has heard 100 times before. Track the target. Lead it 3 rings. Wheeler swings the massive barrel, trying to estimate where the aircraft will be in the 4 seconds it takes a 5-inch shell to travel 3,000 yards. He's fired at Japanese aircraft 17 times in the past 6 months. He's never hit one, not once. His shells always explode. Behind the target, puffs of black smoke marking where enemy aircraft used to be, not where they are. But today is different. Today, Wheeler's shells are fitted with something the Navy calls variable time fuses, though everyone aboard Helena uses a different name, the funny fuse. Wheeler centers his sight, fires, and watches his shell streak toward empty sky 200 feet ahead of the diving bomber. The Naval flies directly into that seemingly empty space. The shell doesn't need to hit. 75 feet, a miniature radar transmitter inside the warhead senses the metal aircraft and detonates. The explosion creates a lethal fragment pattern 3,000 square feet in area. The Naval disintegrates. Wheeler stares at his gun barrel, then at Chief Desmond, then back at the burning debris falling toward the ocean. For 6 months, he's aimed at targets and missed. Today, he aimed at nothing, at a ghost that didn't exist yet, and the ghost became devastatingly real. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Across the Pacific Theater in early 1943, American naval gunners faced a mathematics problem that training couldn't solve. To understand their frustration, you must first understand the geometry of anti-aircraft fire. A 5-inch 38 caliber gun fires a 55-pound shell at 2,600 feet per second. Fast by artillery standards, but not instantaneous. The shell requires approximately 4 seconds to reach a target at 3,000 yards, the typical engagement range for Japanese torpedo bombers approaching American task forces. During those 4 seconds, an enemy aircraft traveling at 250 miles per hour moves nearly 1,500 feet, more than a quarter mile. A bomber maneuvering at 300 miles per hour covers nearly a third of a mile. The gunner must aim not at the aircraft, but at a point in empty space where the aircraft will be when the shell arrives. The calculation requires knowing the target's exact speed, heading, altitude, and rate of turn, variables that change constantly as pilots take evasive action. Before 1943, American gunners used time fuses, mechanical devices set to detonate at a predetermined altitude calculated by the ship's fire control computer. The Mark 37 Director, a sophisticated instrument mounted high on the ship's superstructure, used optical rangefinders and mechanical computers to estimate target position. Operators inside the Director tracked the aircraft through telescopic sights, while the Mark I fire control computer, a 3,000-pound electromechanical calculating machine, processed the data and transmitted elevation and bearing commands to the guns. The system represented the pinnacle of pre-war fire control technology. It was also hopelessly inadequate. The fundamental problem lay in the time, fuse itself. Naval shells used mechanical clockwork fuses that began timing the moment the shell left the barrel. The ship's fire control team set these fuses based on the computed time to target, typically between 3 and 6 seconds for anti-aircraft work. If the calculation was perfect, and the aircraft maintained exactly the same course, speed, and altitude, the shell would explode near enough to damage the target with shrapnel. But aircraft don't fly in straight lines during combat. Japanese pilots, veterans of hundreds of combat missions dating back to the invasion of China in 1937, knew exactly when to brake, turn, or dive to spoil American fire control solutions. They watched for muzzle flashes from American ships and immediately altered course. By the time the shells reached their detonation point, the aircraft had moved somewhere else entirely. The statistical results were devastating. In 1942, U.S. Navy 5-inch guns averaged 654 time-fused shells for each enemy aircraft shot down, 654 rounds. A single 5-inch shell weighed 55 pounds and cost approximately $18, nearly $300 in today's money. Shooting down one Japanese bomber required expending roughly $12,000 in ammunition alone, assuming perfect supply logistics and unlimited time. During the carrier battles of 1942, the Coral Sea, Midway, and the Eastern Solomons, American task forces often exhausted their anti-aircraft ammunition repelling Japanese attacks. Ships would return to Pearl Harbor or Noumea with their magazines nearly empty, having fired thousands of rounds for handfuls of confirmed kills. The carriers Lexington, Yorktown, Hornet, and Wasp all fell to Japanese air attack, their defensive batteries unable to stop determined bomber crews willing to press attacks through walls of anti-aircraft fire. Gunner's mate Tom Wheeler experienced this failure, personally during the Battle of the Eastern Solomons in August 1942. Helena's 5-inch battery engaged a formation of 18 Betty bombers attacking the carrier Enterprise. Wheeler's mount fired 63 rounds during the 20-minute engagement. Post-battle analysis credited Helena's entire battery, all 15 5-inch guns firing over 300 shells, with contributing to the destruction of 2 enemy aircraft. 2 confirmed kills for 300 rounds, a hit rate of 0.6%. Wheeler knew his gunnery technique wasn't the problem. He'd scored expert ratings at Fleet Gunnery School in San Diego. He understood deflection shooting, could calculate lead angles in his head, and maintained his equipment with obsessive precision. The problem was that human minds, even well-trained ones, couldn't process the necessary calculations fast enough. By the time Wheeler adjusted his aim to compensate for a target's turn, the target had turned again. The psychological impact extended beyond mere frustration. American sailors watched Japanese bombers line up for torpedo runs, knowing their defensive fire would likely miss. They watched shipmates die in explosions that adequate anti-aircraft fire might have prevented. Morale suffered. Why practice gunnery if the weapons couldn't hit their targets? Why maintain equipment if the equipment was fundamentally inadequate? Admiral Harold Bowen, head of the Navy's Research and Development Division, understood the crisis. In June 1940, as France fell and Britain fought for survival, Bowen met with representatives from the National Defense Research Committee to discuss emerging threats to surface ships. The meeting's focus was direct. How do we stop aircraft from sinking our fleet? The answer lay in 2 separate innovations that would eventually combine into the most effective anti-aircraft system of World War II. The first innovation, the proximity fuse, originated in British research. The second, the lead computing Gunsight, emerged from a secret laboratory at MIT. Neither technology was completely new. Inventors had suggested proximity fuses dating back to the 1920s. Gyroscopic gunsights had existed in prototype form since the mid-1930s, but transforming theoretical concepts into reliable weapons that could withstand the violence of naval combat required solving engineering problems that had defeated previous attempts. The proximity fuse development began in earnest in August 1940, when the Navy established Section T of the Applied Physics Laboratory at Johns Hopkins University under Dr. Merle Tuve. Their mission was simple to state and extraordinarily difficult to execute. Create a fuse that knows when to explode. The conventional approach used acoustic triggers, microphones set to detect aircraft engine sounds. But engine noise varied wildly depending on distance, angle, and atmospheric conditions. Photoelectric fuses, using light-sensitive receptors, worked better, but required line of sight to the target and failed in darkness or clouds. Dr. Tuve's team pursued a third option, radio proximity detection. The concept was elegant. Install a miniature radio transmitter and receiver inside the fuse. The transmitter broadcasts a continuous signal. When the shell approaches within lethal range of a metal object, the reflected signal increases in strength. When that strength reaches a predetermined threshold, a circuit closes, detonating the explosive. Simple in theory. Impossible in execution, or so it seemed. The challenges were extraordinary. The fuse needed to survive acceleration forces of 20,000 Gs when fired from a 5-inch gun, 20,000 times the force of gravity, applied in the milliseconds between rest and muzzle velocity. The impact would shatter conventional radio tubes, vacuum tubes, and electrical components. The fuse needed to withstand rotation. Hundreds of revolutions per second for stabilization, creating centrifugal forces that would destroy normal electronics. The fuse needed to operate reliably in temperatures ranging from -40 degrees at altitude to +120 degrees in ship magazines. It needed to resist saltwater corrosion, shock from rough handling, and vibration during transport. It needed to be small enough to fit inside a shell nose, typically no more than 3 inches in diameter. It needed to be cheap enough for mass production, simple enough for rapid manufacture, and reliable enough that gunners would trust it in combat. Most challenging of all, it needed to differentiate between aircraft and ocean waves. A shell fired at a low-altitude target would pass close to the water's surface, where wave crests might trigger premature detonation. The fuse required sophistication to distinguish metal aircraft from water, yet simplicity to survive combat conditions. Dr. Tuve's team worked through 1940 and into 1941, testing dozens of designs. Early prototypes failed catastrophically. Vacuum tubes shattered during firing. Transmitters stopped broadcasting after acceleration. Batteries leaked or exploded. Detonators fired prematurely or not at all. The breakthrough came when engineers at Sylvania Electric developed specialized miniature vacuum tubes capable of withstanding gun launch. These rugged tubes, smaller than a thumb and reinforced with shock-resistant materials, could survive 20,000 G acceleration and maintain functionality through hundreds of rotations per second. Sylvania eventually employed 10,000 workers, mostly women, manufacturing these precision tubes at a rate of 1 million every 2.5 days, 2/3 the output of the entire American pre-war radio industry. By May 1941, Section T had a working prototype. The Mark 32 proximity fuse contained a miniature radio transmitter broadcasting at nearly 200 megacycles, a receiver tuned to detect reflected signals, a battery power supply, and a detonator circuit. The entire assembly weighed less than 3 pounds and fit inside a standard 5-inch shell nose. In June 1941, the Navy conducted live-fire tests at the Dahlgren Proving Ground in Virginia. Remote-controlled drone aircraft flew predetermined patterns while destroyers engaged them with proximity-fused shells. The results exceeded every expectation. During 3 days of testing, gunners brought down all test drones with minimal ammunition expenditure. Shells that would have missed by 100 feet using time fuses now detonated within lethal range, their fragment patterns shredding drone airframes. The Navy cancelled the remainder of the scheduled tests and immediately ordered mass production. But production was only half the challenge. The proximity fuse represented technology so advanced that its very existence was classified at the highest level. If the enemy captured an intact fuse and reverse-engineered it, they could deploy the same technology against American aircraft. Security measures were extraordinary. The fuses received the innocuous designation variable time, abbreviated VT, to obscure their true function. Technical manuals referred to them as VT fuses, never proximity fuses. Production facilities operated under armed guard. Workers knew only their specific assembly tasks, never the complete design. Shell handling crews received minimal information, simply that VT-fused ammunition required careful treatment and should never be fired where intact duds might be recovered by the enemy. The combined chiefs of staff issued a direct order. No proximity-fuzzed weapons could be used over land where unexploded shells might fall into enemy hands. The technology was too valuable to risk compromise. This restriction meant proximity fuses would debut exclusively in naval combat over open ocean, where duds would sink beyond recovery. The restriction also meant the Army Air Force, desperately needing better anti-aircraft protection for bomber formations over Europe, couldn't access the technology. General Henry Hap Arnold protested, arguing that improved anti-aircraft fuses could save hundreds of bomber crewmen. The chiefs of staff remained adamant. No VT fuses over land until the risk of capture became acceptable. By December 1942, Crosley Corporation, RCA, General Electric, Eastman Kodak, and other contractors were manufacturing proximity fuses at a combined rate of 500 per day. The first operational batch, 5,000 rounds, shipped to the South Pacific in late December, distributed to Enterprise, Saratoga, and Helena. The fuses arrived with minimal documentation and strict security classification. Gun crews received basic instruction: set the fuse normally, track the target normally, fire normally. The fuse will handle detonation. Don't discuss this equipment with anyone lacking proper clearance. Gunner's mate Wheeler attended the brief training session aboard Helena in late December 1942. His chief gunnery officer, Commander Robert Stanton, provided the only explanation Wheeler would receive. These new fuses use technology I'm not authorized to explain. What you need to know is this: you no longer aim at the target. You aim ahead of the target, same as always. But instead of hoping your time fuse detonates at the right altitude, this fuse will detonate automatically when it gets close enough to damage the target. Your job remains unchanged: track smoothly, maintain proper lead, and fire when the director gives the command. The fuse does the rest. Wheeler studied the shells marked with distinctive VT markings. They looked identical to conventional ammunition except for the nose fuse assembly, which seemed slightly more complex. The shells weighed the same, balanced the same, loaded the same. Nothing in their external appearance suggested revolutionary technology. On January 5, 1943, Wheeler would discover exactly how revolutionary that technology was. The morning dawned clear and hot, typical weather for Guadalcanal in early January. Helena steamed as part of Task Force 18, a cruiser-destroyer group conducting anti-shipping sweeps through the Solomon Islands. American forces had secured Henderson Field 3 months earlier, but Japanese air bases at Rabaul, 250 miles northwest, remained operational and dangerous. Intelligence predicted enemy air activity. It was simply a matter of when, not if. The attack came at 10:15 hours. Radar operators detected a small formation of aircraft approaching from the northwest at 15,000 feet. Fighter direction officers scrambled Wildcat fighters from Henderson Field, but the Japanese formation, 9 Naval dive bombers with 0 escort, reached attack position before the interceptors could engage. Helena's general quarters alarm screamed through steel passages. Wheeler sprinted to his gun mount, arriving breathless as the first enemy aircraft began their dives. The Vals attacked in the classic Japanese dive bombing pattern, 3 aircraft sections diving in sequence from different angles to split the American defensive fire. Wheeler's mount tracked the first bomber through its dive, the fire control director transmitting continuous bearing and elevation updates. Chief Desmond called the ranges as they decreased. 4,000 yards, 3,500, 3,000. At 3,000 yards, the director ordered fire. Wheeler's gun erupted, the 55-pound shell leaving the barrel at 2,600 feet per second. He didn't see where it went. His training demanded immediate attention to the next shell, the loading crew already ramming another round into the breech. The gun fired again, and again. 6 rounds in rapid succession as the Val continued its dive toward the destroyer formation. Then Wheeler saw it. The 4th shell, traveling through seemingly empty air 200 feet ahead of the diving bomber, suddenly exploded in a brilliant flash. No visible impact. No near miss, just a detonation in empty sky. The Val flew directly through the explosion's fragment pattern. 20mm shell fragments, traveling at supersonic velocity, shredded the bomber's engine cowling, punctured fuel tanks, and severed control cables. The aircraft's nose pitched down violently. The pilot never recovered. The Val augured straight into the ocean, throwing up a geyser of white water. The entire engagement lasted 12 seconds from first shot to impact. Wheeler had fired 6 rounds. 1 kill. The mathematics had fundamentally changed. But Wheeler didn't have time to process what he'd witnessed. 2 more Vals were diving, their fixed landing gear and bomb shapes clearly visible. His mount engaged the second bomber at 3,500 yards, firing 4 rounds. The 3rd shell detonated close enough to blow off the Val's left wing. The bomber spun into the sea. Across Helena's deck, other gun mounts reported similar results. The starboard-forward mount destroyed a Val with 2 shells. The port-aft mount killed another with 3. By the time the attack ended, 4 minutes after it began, Helena's gunners had claimed 5 confirmed kills from 23 proximity-fused shells fired. 5 kills from 23 rounds. A hit rate exceeding 20%, 30 times better than time-fuzzed ammunition. The improvement wasn't limited to Helena. Across the task force, cruisers and destroyers equipped with VT fuses reported unprecedented accuracy. The destroyer Fletcher claimed 3 kills from 14 rounds. The cruiser San Francisco destroyed 2 bombers with 8 shells. The mathematical transformation was immediate and undeniable. The Navy had solved the detonation problem. Shells no longer needed to explode at exactly the right altitude, through precise calculation. They needed only to pass within lethal range, and the fuse would handle the rest. But solving one problem revealed another, equally fundamental limitation. The proximity fuse made shells more lethal, but it didn't help gunners aim. Wheeler still needed to estimate lead angles, still needed to predict where a maneuvering aircraft would be seconds in the future. The VT fuse expanded the margin for error. A shell passing within 75 feet would now detonate instead of sailing harmlessly past. But within 75 feet still required accurate initial aiming. If Wheeler aimed 200 feet behind a target, even a proximity fuse couldn't save the shot. American gunners needed help with the aiming problem, and that help was already under development, though through a completely separate research program. The solution would come from an MIT professor who specialized in gyroscopic instruments and had no formal connection to naval weapons development. Dr. Charles Stark Draper ran the instrumentation laboratory at MIT, a small research group focused on aircraft navigation systems. In early 1941, Draper was working on gyroscopic stabilization for bomber gunsights when he realized the same principles could revolutionize naval anti-aircraft fire. The concept was similar to the K-14 computing gunsight being developed for Army Air Force fighters. Use spinning gyroscopes to detect the gunner's rate of turn while tracking a target. The gyroscopes, spinning at thousands of revolutions per minute, resist any change in their orientation. When a gunner swings his weapon to follow a moving aircraft, the gyroscopes lag behind, their resistance to change creating measurable angular displacement. That displacement, combined with the target's estimated range, provides all the information needed to calculate proper lead angles. Draper's innovation was adapting this fighter pilot technology for use by naval gunners. Fighter planes provided relatively stable platforms, aircraft flying straight and level while tracking targets. Naval guns operated on ships that rolled, pitched, and yawed in heavy seas, while the entire vessel maneuvered at speed. The gyroscopic sight needed to distinguish between ship motion and target motion, calculating lead angles while compensating for the unstable platform. Draper's prototype, which he'd been developing since late 1940, looked deceptively simple. A rectangular black metal box, barely larger than a shoebox, contained 2 precision gyroscopes mounted perpendicular to each other. One gyroscope detected horizontal turning motion, the other sensed vertical motion. Electric motors, powered by the ship's electrical system, kept both gyroscopes spinning at 18,000 revolutions per minute. The sight projected its aiming solution onto a piece of angled glass that the gunner looked through. Unlike the fixed reticle of conventional sights, Draper's system displayed a moving aiming point that danced across the gunner's field of view, automatically positioning itself where the target would be when bullets arrived. The gunner's job became almost childishly simple. Keep the moving aiming point on the target and pull the trigger. The gyroscopes handled all the mathematics, but Draper faced the same challenge that plagued proximity fuse development. Creating a prototype in a laboratory was one thing. Building a device that could withstand naval combat was entirely different. Gyroscopes are delicate instruments. The bearings that allow smooth rotation at 18,000 RPM require precision machining and careful assembly. Salt spray corrodes electrical contacts. Shock from nearby gunfire could knock gyroscopes off their bearings. Temperature extremes affected motor performance. Draper solved these problems through obsessive attention to detail and unconventional engineering. He sealed the gyroscopes in waterproof housings filled with dry nitrogen to prevent corrosion. He mounted the entire assembly on rubber shock absorbers to isolate it from vibration. He used jeweled bearings, the same type found in expensive watches, to minimize friction and maximize reliability. The result was a computing gun sight that could survive being bolted to a 20mm or 40mm anti-aircraft gun and function reliably through hundreds of hours of combat. By May 1941, Draper had a working prototype ready for demonstration. Commander Marion Murphy, head of the Navy's Fire Control Section, visited MIT on May 28 to witness the device in action. What Murphy saw convinced him immediately. Draper mounted the sight on a test weapon and tracked aerial targets, while Navy observers watched the moving reticle predict target position with uncanny accuracy. The psychological shift was profound. Instead of wrestling with mental calculations while tracking a fast-moving target, the gunner simply followed a glowing aiming, a point that moved automatically. The machine did the thinking, the human did the tracking. Murphy telephoned Sperry Gyroscope Corporation the next day and requested engineering specifications for 50 prototype sights. The Navy designated Draper's invention the Mark 14 Gunsight. By August 1941, Sperry had received contracts for 12 experimental units, the first of what would eventually total 85,000 Mark 14 gunsights produced during the war. Production began slowly. The Mark 14 required precision components that took time to manufacture. Each sight contained over 200 machined parts. The gyroscopes alone required specialized equipment and skilled workers, but by mid-1942, Sperry's Brooklyn factory was producing Mark 14s at increasing rates. The first operational gunsights reached the Pacific Fleet in late 1942, installed on 40mm Bofors guns aboard destroyers and cruisers. These medium-caliber weapons formed the second line of anti-aircraft defense, engaging targets that penetrated the long-range 5-inch gun envelope. At ranges between 1,000 and 3,000 yards, the Bofors guns threw up walls of explosive shells, their high rate of fire, 120 rounds per minute per gun, creating overlapping fields of fire. But like the 5-inch guns, Bofors' effectiveness depended entirely on accurate aiming. A 40mm shell travelled at 2,800 feet per second, fast enough to reach most targets within 2 seconds. During those 2 seconds, an aircraft travelling at 300 miles per hour moved nearly 900 feet. The gunner needed to lead his target by that distance, adjusting continuously as the aircraft manoeuvred. With conventional iron sights, achieving this level of precision required natural talent combined with extensive practice. Most gunners couldn't do it consistently. The Mark 14 changed everything. Gunner's mate 3rd Class Robert Patterson, assigned to a quad 40mm mount aboard the destroyer Nicholas, received his first Mark 14 in December 1942. Patterson had been firing the Bofors since August with mediocre results. His mount had engaged Japanese aircraft on 7 occasions, expending over 800 rounds for 0 confirmed kills. Patterson was accurate enough to scare enemy pilots into breaking off attacks, but not accurate enough to actually destroy aircraft. The Mark 14 installation required 2 days. Technicians mounted the sight on the gun director, a pedestal-mounted aiming device that allowed the operator to track targets while transmitting pointing commands to the gun mount. The sight itself weighed 13 pounds, about the same as the gun director's original optics. Its rectangular housing looked crude compared to polished brass and optical glass, but its functionality exceeded anything Patterson had seen. The training lasted 30 minutes. A Sperry representative explained the operation in practical terms. See these handlebars? You use them to track the target, same as before. See this knob? You dial in the target's wingspan. 30 feet for a 0, 40 feet for a Betty, whatever you're shooting at. The sight will automatically calculate the lead angle and display it as a moving pip in your view. Keep the pip on the target. When you're tracking smoothly, squeeze the trigger on the right handlebar. The guns will fire where the sight tells them to. Patterson practiced on towed targets for 2 days, learning to trust the sight's calculations over his instincts. The hardest part was psychological. The moving pip often appeared to float in empty sky, dozens of feet ahead of the actual aircraft. Every fibre of Patterson's training screamed that he was aiming wrong, that his bullets would miss by enormous margins. But the math never lied. When Patterson kept the pip centered on the target and fired, his tracers converged exactly where the pip predicted, exactly where the target flew moments later. His first combat test came on February 1st, 1943, during a Japanese torpedo bomber attack near Rendova Island. 3 Bettys approached Nicholas at low altitude, skimming 30 feet above the waves to avoid radar detection. By the time lookouts spotted them, the bombers were inside 3,000 yards, well within the Bofors envelope. Patterson swung his director onto the lead Betty, dialed 40 feet into the wingspan selector, and watched the Mark 14's moving pip appear in his sight picture. The pip floated 40 feet ahead of the bomber's nose, dancing in empty air. Patterson tracked the target for 3 seconds, letting the gyroscopes stabilize, then pressed the firing trigger. 4 40mm guns erupted simultaneously, their barrels elevated and trained according to the Mark 14's calculations. 100 explosive shells per second streamed toward the point where the Betty would be. The bomber flew directly into the converging fire. Shells designed to explode on impact shredded the aircraft's engines, fuselage, and wings. The Betty disintegrated, flaming wreckage cartwheeling across the water. Total time from initial tracking to kill, 8 seconds. Total rounds expended, approximately 240, less than 3 seconds of sustained fire. Patterson engaged the second Betty immediately, destroying it with another 3-second burst. The third bomber, seeing its companions obliterated, dropped its torpedo prematurely and fled. Patterson's mount had just achieved in 20 seconds what previously required extended engagements expending thousands of rounds. The Mark 14 hadn't just improved accuracy, it had transformed the fundamental nature of naval anti-aircraft combat. Across the Pacific Fleet, ships equipped with Mark 14 sights reported similar results. The destroyer Fletcher claimed 4 confirmed kills in March 1943, all achieved with Bofors guns firing Mark 14 directed fire. The cruiser San Diego destroyed 6 Japanese aircraft in April, its 40mm battery accounting for 4 of the kills. Statistical analysis showed that Bofors guns equipped with Mark 14s required approximately 300 rounds per kill, compared to over 2,000 rounds for guns using iron sights. The improvement factor, nearly 7-to-1, represented a revolution in defensive effectiveness. But the true revolution occurred when the Navy combined both technologies, VT proximity fuses in the 5-inch guns for long-range defense, Mark 14 computing sights on the Bofors guns for medium-range defense. Together, these systems created a layered defense that Japanese pilots found nearly impossible to penetrate. The tactical sequence worked like this. Radar detected incoming raids at ranges exceeding 50 miles, providing early warning and time to scramble fighters. At 10 to 15 miles, the 5-inch guns opened fire, their VT-fused shells creating aerial minefields that forced enemy formations to break up. Aircraft that survived this long-range fire entered the medium-range envelope at 3,000 yards, where Mark 14 directed Bofors guns engaged with devastating accuracy. Any aircraft that penetrated to 1,000 yards faced close-range 20mm fire, also increasingly equipped with Mark 14s, creating a final wall of lead. Japanese pilots described attacking American task forces as flying through layers of progressively more accurate fire, each layer more deadly than the last. The statistical impact proved overwhelming. In 1942, American ships in the Pacific fired an average of 654 5-inch rounds per aircraft destroyed. By mid-1943, after VT fuse deployment, that number dropped to approximately 500 rounds per kill. By late 1943, with VT fuses and improved fire control, the number fell to 300 rounds per kill. The improvement represented a doubling of effectiveness. For the 40mm Bofors guns, the transformation was even more dramatic. In 1942, Bofors batteries fired an average of 2,200 rounds per kill. By mid-1943, with Mark 14 sights installed, that number dropped to 400 rounds per kill, a 5-fold improvement in accuracy. The strategic implications extended far beyond ammunition savings. Improved anti-aircraft fire meant fewer successful attacks. Fewer successful attacks meant fewer ships damaged or sunk. Fewer ships lost meant more combat power available for offensive operations. The Navy's ability to project power across the Pacific depended entirely on keeping carriers, cruisers, and destroyers operational. Every ship that survived a Japanese air attack represented hundreds of millions of dollars in preserved combat capability, and thousands of sailors' lives saved. Admiral Raymond Spruance, commanding the Fifth Fleet during the Gilbert Islands campaign in November 1943, compiled detailed statistics on anti-aircraft effectiveness. His report, classified at the time but declassified decades later, quantified the revolution in defensive capability. During the Tarawa operation, Task Force 53 engaged Japanese air attacks on 14 separate occasions over 5 days. Total aircraft shot down by naval gunfire, 67. Total ships lost to air attack, 0. Total ammunition expended, approximately 16,000 5-inch rounds and 48,000 40mm rounds. Spruance's analysis noted that equivalent defences in 1942 would have required firing over 100,000 rounds to achieve 67 kills, assuming such kill totals were even possible with older technology. The math suggested that VT fuses and Mark 14 sights had increased fleet defensive effectiveness by a factor of 6 to 8. But technology alone doesn't win battles. Human factors mattered. Gunner's mate Wheeler, gunner's mate Patterson, and thousands of other enlisted sailors needed to trust their revolutionary equipment enough to aim at empty sky and fire at ghosts. The psychological adjustment proved harder than the technical training. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Chief Petty Officer Martin Desmond, Wheeler's gun captain aboard Helena, understood the challenge. In March 1943, after 2 months of combat with VT fuses, Desmond gathered his gun crew for an informal discussion. "I know what you're thinking," Desmond began, addressing the 6 sailors who manned Wheeler's mount. "I know it feels wrong to aim ahead of the target. Your eyes tell you you're shooting at nothing. Your brain tells you you're wasting ammunition. But here's what I need you to understand. The fuse is smarter than you. The sight is faster than you. Your job isn't to outthink the equipment. Your job is to feed it good information. Track smoothly. Maintain proper lead. Let the machines do the mathematics." Desmond pulled out a notebook filled with combat statistics. In 1942, before we had these fuses, our mount fired 1,600 rounds in combat. We got credit for 2 possible kills, both unconfirmed. That's 800 rounds per maybe kill. Since January, we fired 430 rounds. We have 9 confirmed kills. That's less than 50 rounds per kill. The math doesn't lie. When you trust the equipment, it works. The statistics convinced most sailors, but psychological resistance persisted among some experienced gunners. Men who had developed hard-earned skills in deflection shooting, who had learned to estimate lead angles through hundreds of hours of practice, struggled to surrender that expertise to machines. They wanted to aim where their instincts told them, not where glowing pips and computer calculations suggested. This resistance manifested most clearly among senior petty officers and chief petty officers who had fought through the desperate battles of 1942. These men had survived when American defensive fire was hopelessly inadequate. They had watched ships die, seen friends killed by attacks their guns couldn't stop. Many developed superstitions, personal aiming techniques, and mental calculations that helped them cope with inadequate weapons. Asking them to abandon those hard-learned skills felt like asking them to unlearn survival itself. Chief Gunner's mate William Bassett, serving aboard the cruiser Columbia, exemplified this resistance. Bassett had been firing naval guns since 1937. He had fought at Coral Sea, Midway, and Guadalcanal. He could estimate target speed by watching wing shape, calculate deflection angles in his head, and adjust for wind drift through pure experience. When Columbia received Mark 14 sights in March 1943, Bassett refused to use them. "I don't need a machine to tell me where to aim," he told his gun crew. "I've been doing this job for 6 years. I know deflection shooting." For 3 combat engagements, Bassett directed his mount's fire using traditional methods, ignoring the Mark 14 completely. His results were average, consistent with pre-war gunnery standards. His mount expended roughly 2,500 rounds per kill, far better than random fire, but nowhere near the performance of Mark 14 equipped guns. Columbia's gunnery officer, Lieutenant Commander James Morrison, finally confronted Bassett in April. "Chief, I've reviewed the combat reports. Every other mount on this ship is averaging 400 to 500 rounds per kill. Your mount is at 2,500, You're wasting ammunition and reducing our defensive effectiveness. Use the sight, or I'll find someone who will." Bassett reluctantly complied. His first engagement, using the Mark 14, a Japanese bomber attack near Bougainville, produced 2 confirmed kills from 600 rounds fired. Bassett's after-action report was grudging but honest. "The sight works. I don't understand how, but it works." This pattern repeated across the fleet. Experienced gunners resisted. Statistics convinced them. Effectiveness improved. By mid-1943, the cultural transformation was complete. Naval gunners trusted their computing sights the way fighter pilots trusted their K-14 gun sights. They aimed at ghosts and killed real aircraft. The Japanese response evolved throughout 1943 as American defensive capabilities improved. Raid commanders noticed the change first. Attack runs that previously succeeded now failed. Bombers that should have reached release points never arrived. Torpedo planes that should have survived to drop their weapons disintegrated in mid-approach. The mathematics of attack planning had fundamentally changed. Lieutenant Commander Takao Suzuki, an experienced bomber pilot with the Japanese Navy's Air Group 6, survived 3 attacks against American task forces between January and May 1943. His after-action reports, captured after the war, describe growing frustration with American defensive fire. January 8th, attack on American cruiser group near Guadalcanal. Suzuki's report noted accurate long-range anti-aircraft fire, forcing his formation to break up early. American shells explode with remarkable precision, no longer necessary for them to score direct hits. Near misses, now lethal. Lost 3 aircraft before reaching attack position. March 15th, attack on American destroyers near Russell Islands. American defensive fire more accurate than any previous engagement. Medium-caliber guns track targets with machine-like precision. Bullets arrive exactly where aircraft will be, not where aircraft are. Lost 5 of 9 aircraft. No successful torpedo drops. Recommend revising attack doctrines. May 10th. Attack on American carrier task force east of Guadalcanal. American defensive capability now exceeds our ability to press attacks. Long-range fire breaks up formations. Medium-range fire destroys individual aircraft with minimal ammunition expenditure. Close-range fire creates impenetrable walls. Lost 7 of 12 aircraft. No hits scored on American ships. This type of attack no longer viable. Suzuki's observations reached Japanese naval headquarters in Rabaul and eventually Tokyo. Intelligence analysts struggled to understand what had changed. They knew American ships carried radar. They assumed improved fire control computers explained some accuracy gains. But the fundamental transformation, shells that detonated automatically near targets and sights that predicted target position, remained mysterious. The Japanese never captured an intact VT fuse. American security measures ensured that proximity-fused shells fired over water either detonated, destroying the fuse mechanism, or sank into deep ocean beyond recovery. Similarly, the Mark 14 gun sights, bolted to gun mounts that typically went down with damaged ships, rarely survived intact enough for technical analysis. Japanese engineers developed their own proximity fuse technology by late 1944. But production problems and material shortages meant the weapons never reached combat units in meaningful numbers. The technological gap, established in early 1943, persisted through war's end. This gap manifested most clearly during the kamikaze campaign that began in October 1944. Japanese commanders, recognizing that conventional attacks could no longer penetrate American defenses, resorted to suicide tactics. If pilots couldn't survive to drop bombs and escape, they would become the bombs themselves, crashing directly into American ships. The kamikaze attacks, desperate and terrible, posed unique challenges to American defensive fire. Unlike conventional bombers that approached, dropped weapons, and turned away, kamikaze aircraft maintained straight courses directly toward their targets. This simplified fire control solutions. The attacking aircraft flew predictably, making deflection calculations easier. But it also created terrifying urgency. A conventional attack that missed could be engaged again during the exit. A kamikaze that penetrated the defensive envelope would strike its target. American gunners using VT fuses and Mark 14 sights proved remarkably effective against kamikaze attacks, though not perfectly so. The combination of proximity-fired 5-inch shells and computing site-directed Bofors fire created defensive zones that kamikazes found nearly impossible to penetrate. Statistical analysis from the Okinawa campaign, April through June 1945, showed that American ships destroyed approximately 70 to 80% of attacking kamikazes before they could strike. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.